Hello, welcome back to AP Physics. Today we're talking about conservation of energy. And in science we say that energy is conserved. And what do we mean when we say that something is conserved? We don't mean conserve energy as in turn out the light bulbs when you're not using them, quit wasting electricity. We basically mean that the initial amount of energy that you start with is equal to the final amount of energy that you end up with. None of it is created or destroyed. It's all got to show up somewhere. So energy doesn't get produced or vaporized. It just changes from one object to another object. One object can take energy from another object, or energy can change from one form to another form, but it's all got to show up. The joules have got to show up somewhere. For example, if we start with a heavy weight that's elevated, it's starting out with gravitational potential energy. If we cut the string, just before it hits the wooden spike here, we've lost most of our gravitational potential energy, and it's moving fast, which means that energy is in the form of kinetic energy. And then when it hits this wooden stake and comes to a stop, what ends up happening is the weight does work on the stake, and that work transfers that energy into heat. So that heat is where the energy is in the form of now. So work moves energy around and changes energy from one form to another. In other words, energy is like money and work is like spending it. You can spend the energy money in different stores. You can convert it into other types of things, like groceries or whatever, but the money has got to show up somewhere. So just an example here, we're starting with our elevated mass again, and our energy is starting out in the gravitational potential energy store. We've got 4 Bernabo dollars. Okay, if I cut the string, okay, just before it hits the ground, that energy is in the form of kinetic energy, so it's in that store. So we've spent it, but it still shows up. It's just in a different location. And then right when it hits the ground, that energy, thud, gets converted to heat and sound and other forms of energy, not available for it to jump back up into the sky again. So, but no matter what, notice that we still have our 4 Bernabo dollars worth of energy. It's got to show up somewhere. So here's again conservation of energy. So here we've got a ball that's bouncing up into the air. When it's in the top of its peak, the energy is in the form of gravitational potential energy. And then as you can see, it's speeding up as it reaches the ground as the spacing gets further apart. When the ball actually is in contact with the ground, it's squished, and that energy is in the form of elastic potential energy, and that's what gives it the energy to bounce back up and rebound and jump back up into the air again. So to write this in the form of an equation, total initial energy equals total final energy, we can just write it as U1, or my initial potential energy plus my initial kinetic energy equals my final potential energy plus my final kinetic energy. So the Bernabo dollars have to show up somewhere. Some of these can be zeros, and usually some of them will be zeros, but the energy has got to show up somewhere. So just to throw some numbers at this, here we've got a person at the top of a big tall tower. They're starting out with 10,000 joules of gravitational potential energy, and initially their kinetic energy is 0 because they're not moving. As they fall, they lose some of their gravitational potential energy because their height decreases, mgh, and what they lose in potential energy, they gain in kinetic energy. Notice that the total still adds up to 10,000. When they're halfway down, they've lost half of their gravitational potential energy, and that 5,000 joules that they lost in PE shows up as KE, and et cetera, et cetera. And just before they hit the ground, they have 0 joules of potential energy, and all of their Bernabo dollars of energy are in kinetic energy. They've got 10,000 joules of kinetic energy. So the total amount is conserved. The total amount stays the same. So picture this as a pendulum that's swinging back and forth. And so here I've got it pictured at different points in its swing. So here it's at the top of its path. Here it's swung down a little bit. Here it's at the bottom of its path, moving the fastest. And here it's swung back up. So again, just throwing some numbers at this, if we start off with 100 joules of gravitational potential energy, and we lose 25 joules or we lose 75 joules of potential energy, that 75 joules has got to show up as kinetic energy. So again, notice I still have 100 joules of energy. When it's at the bottom, all of the joules of potential energy are now kinetic energy. And then if it doesn't lose any energy to heat, it swings back up to the same height, and we're back into 100 joules of potential energy. So working this with some the equations a little bit. Let's say we've got a ball and it's a mass m, and it rolls down a frictionless incline. So we're not losing any energy to heat, is what we're saying. So all of our energy is going to show up as in one of these forms, potential or kinetic. When we add friction, that'll mess up the scales a little bit, but we'll learn how to deal with that. So all of our energy is going to show up. Whatever we start out with is going to end up at the end here. So what is its velocity at the bottom? So notice that we're looking at a state. Okay, we're considering this to be our state of a height of h, and we're considering this to be our height of 0. So this is our ground energy state as far as the gravitational potential energy. This could, slope on further down, but we would know about it just from what we're looking at. It doesn't matter from where we're looking at, because all we need to know is this state and this state. So what is its velocity at the bottom? So let's look at our equation. So our initial potential energy plus our initial kinetic energy equals our final potential energy plus our final kinetic energy. Well, initially it's got potential energy only in the form of gravitational. There's no elastic potential energy or spring energy. So it's mgh, okay, is its potential energy. It doesn't have any kinetic energy to begin with. Okay. When it's at the second picture, it's at the bottom of the hill, so it doesn't have any height. It doesn't have any potential energy, but its energy is in the form of kinetic energy. So if we notice that the m's will cancel out here, so the m's cancel out. So v squared equals 2gh. Okay, and then solving for v, we get v equals the root of 2gh. So our velocity is equal to the square root of 2 times gravity times our height. Notice that the mass cancel out. And basically what we're looking at is things fall at the same rate regardless of their mass on a given planet. Which we already knew from a previous unit. And to make another connection, so this is the equation that we just came up with for an object falling down or rolling down, or a pendulum swinging down, or anything where we're converting gravitational potential energy into kinetic energy. If we take this equation from unit 1 and we say my initial velocity was 0, which is what we said in our picture when we made this, we get v equals the square root of 2 times a times the displacement. So that's where this equation came from, was conservation of energy. And again, notice that we only needed to know what it was like in this state and what it was like in this state. We didn't need to know what happened in between. That's because energy is what's called a state function, and it just matters the initial state and the final state. I could have shaped this curve any way I wanted to. I could have made it a simple sloping curve. I could have made it a straight line. And it really wouldn't matter what happened between points A and points B. It only matters what it's like at point A and what it's like at point B. Okay, so if I were to ask you a question, here we've got two balls, and they're on different slopes, and I asked you which was moving and which one had a faster velocity when it reached the ground. Okay, well, all we need to know is that v equals the square root of 2gh, and they both have the same height, which means they're both going to have the same velocity. They both start out with identical potential energies, and they're going to end up with identical kinetic energies. So now, if the red ball was twice as heavy, okay, what would happen? Well, remember from before that the mass canceled out, and it doesn't matter. Or in other words, things fall at the same rate, independent of their mass. Okay. So total energy is constant. So if we look at a roller coaster is a good example of conservation of energy. Again, if we start out at the top of a hill, we've got we're starting out with gravitational potential energy. As we go down the hill, we're losing height, we're losing gravitational potential energy. That's getting converted to kinetic energy. When we're at the bottom, it's all kinetic energy, assuming that I consider this bottom part to be my ground state, my zero height, which you usually, you always need to consider one elevation to be your zero height. And we're considering this to be my zero height right here. Although it could technically still be elevated off the ground, which it actually looks like it is, if that makes any sense. So, and then as we roll back up the hill, we're slowing down, we're losing kinetic energy, and we're gaining gravitational potential energy, and then et cetera, et cetera. Okay, so when will the roller coaster be moving the slowest? Well, it's going to be moving the slowest when it's got the most gravitational potential energy and the least kinetic energy, which would be at the top of the hill. But we already kind of knew that anyway. Okay, when will it be moving the fastest? Okay, we already know it's going to be at the bottom of the hill down here, and we know that from physics because it's going to have the least potential energy because it's got the least height, and therefore it's going to have the most kinetic energy and the most speed. So anytime it's at the same elevation, it'll be moving at the same speed, assuming that we're not losing any energy to friction. Now, when we lose energy to friction, we're not destroying it. We're just converting it to another form, and we'll talk more about that later. So here let's work a problem. We've got a pendulum. It's got a mass of m kilograms. It's attached to a 25 centimeter string. We release it from an angle of 25 degrees C with respect to the ceiling. How fast will it be traveling at the bottom of its path? So let's take a look at that. So here's our picture. We're starting with an angle of theta, and so our string length is L. We just called it L, and so we know that when it swings down, it's going to drop down a distance of h. Okay, that's going to be how far it falls, and that's going to be what determines how fast it's moving is this distance h that it falls. Not necessarily how high it starts out with, but how far it falls down. So if we use a little basic trig, we know that this side here will equal the sine of theta L. Okay, this side right here, and this is L. So the difference between these two is going to be the distance that it falls down. So that's going to be L minus sine of theta L, and that's going to be the height that it falls. So just getting that out of the way before we get into conservation of energy. So we're going to look at this in terms of conservation of energy. So U1, so our initial potential energy plus our initial kinetic equals our final potential plus our final kinetic. The initial potential energy that we're starting out with is gravitational potential energy. There's no spring energy or anything, and that's mgh. Okay. Our kinetic energy initially is 0, so we just leave that as 0. Now at the bottom of its swing, we're going to say that's my 0 potential energy elevation, so we consider this to be our 0. And that's going to plus my final kinetic energy. So mv squared over 2. So gh equals v squared over 2. Substituting in for h, we get g times L minus sine of theta L. So substituting in for h, and solving, we get that as our equation. So v equals the root of gl, 1 minus theta times 2. And then sticking in numbers, we get 1.68 times, or 1.68 meters per second is how fast it would be moving. So if I were to ask you a question like this, like on a multiple choice test, and I asked you, we've got frictionless ramps, aka we're not losing any energy to friction, we're not losing any energy to heat. I've got a steep ramp, and I've got a longer ramp, okay, both at the same height. but having different horizontal distances. And I asked, compare the speeds. Which of these would be moving faster when it reaches the bottom? Not which is going to reach the bottom first, okay, because that would be the top one would reach the bottom first. We're not asking that. We're asking which is be moving faster when it reaches the bottom. And that answer would be the same because they're both starting out the same elevation. So again, it's a state function. They both start out with mgh. They're both going to end up with mv squared over 2. So it doesn't really matter what happens in between. So here we've got a roller coaster. It starts out at an initial elevation of 20 meters, rolls down to 15 meters, then reaches the quote-unquote bottom at 0 meters, and then rolls back up to 15 meters. And the question, and this is a frictionless roller coaster, and the question is, how fast is it moving at points A, B, and C? I'm just going to work points A and C, and we'll just mention point B. So let's take a look at it. So this is going to be my initial state. You always have to look at an initial state and then a final state. That's key. So my initial state is going to be this one right here, and then my final state is going to be point A. And if we wanted to look at point B, that we'd make point B my final state, but we're looking at point A. So what we want to say is my initial potential energy plus initial kinetic equals my final potential energy plus my final kinetic. So my initial potential energy is in the form of gravitational potential energy, which is mgh, h1, plus 0 kinetic energy. Now at this final state, I still have some gravitational potential energy, so I can't leave that 0. So that's going to be mgh2, and then plus the kinetic energy, which is going to be the difference between the two. So notice again that m's cancel out, which is a pretty common theme here. And so plugging in our numbers. Now notice what I considered this to be my 0 energy state, my 0 elevation state. You always have to consider one elevation to be your 0 state. I could have considered this to be my 0 elevation state and said that my height was 5, and I would have gotten the exact same answer as what I'm going to get here, and I'll show you why. So plugging in, we get g times 20. My initial height is 20. Plus 0 equals g times 15 plus v squared over 2, and then solving for v, we get the square root equals 2g times 20 minus 15. So really all we're doing is we're subtracting these initial heights. That's all we're doing is looking at the difference in elevation between these two. So I could have considered this to be 0 and this to be 5, and I would have gotten the same answer. And so solving, we get 9.9 meters per second. Now, I'm going to get my exact same answer over here too, looking at this state, because I've got the same elevation. I'd have the same kinetic energy. We're not working this one, but we would have just considered H2 to be 0 at this, and it would all be in the form of kinetic energy. But we'd still have our 9.9 meters per second here, assuming we didn't lose any energy to friction. Okay, a cannonball is fired from a cliff at 35 meters per second at 60 degrees above the horizontal. If the cliff is 130 meters tall, how fast is the cannonball moving when it hits the ground below? Okay, so we're in conservation of energy, so we can probably figure that we're going to use conservation of energy to solve this, rather than our initial equations, that we got in Unit 1, which we could certainly use. It would just be a lot more work. So we've got a cannonball. We want to look at our initial energy and our final energy. So our initial potential energy is going to be the height, mgh, which is going to be the height's going to be 130. We do have kinetic energy because the cannonball is moving. So we've got mv squared over 2 in our initial. Okay. Now, when it reaches the ground below, my potential energy is going to be 0, and then it's going to have and then it's all going to be in the form of kinetic energy down here. So notice again that our m's cancel out. Pretty common to have this happen unless we start adding springs into the equation. When we start adding springs, we won't be able to cancel that out. Just looking at the equation without the m's, we get 9.8 times 130, that's our height. We've got 35 squared over 2, that's for our kinetic energy component, equals v2 squared over 2. And so we get, I believe that looks like it's 61.4 meters per second. And so what we want to point out here is that the energy is not a vector. It doesn't matter that it was pointed at 60 degrees above the horizontal or whatever. Energy does not have a direction. So all that mattered is the state. It was its initial potential and its initial kinetic. And then all we have to do is look at the final potential and the final kinetic. So we didn't have to know that here. So that's kind of the main point behind that exercise. Let's throw some springs in the mix. So here we've got a 5 kilogram rock on a spring, and it's compressed a quarter of a meter below its natural state, its unstretched or deformed state. What we want to do is figure out how fast the ball is moving right when it reaches the unstretched or uncompressed state, and then we want to figure out how high that rock is going to go once it's released from the spring. Okay, and again, so what we want to do is look at what's our initial energy and what's our final energy. So initially, we've got spring energy. Okay, do we have any gravitational potential energy? No, because this is my lowest state. I'm going to consider that to be my zero energy. Do we have any kinetic energy? No, because it's initially stationary. So we're going to have just the spring energy. Now when it's in this state, does it have any spring energy? No, because the spring is uncompressed. Okay, will it have any gravitational potential energy? Yes, because it's now elevated above where it started. Okay, will it have any kinetic energy? I think it'll be moving. Okay, it'll be moving. So going back to our equation, so our initial state, we said we had spring energy, kx squared over 2, plus my initial kinetic energy was 0. And we said in that final state we will have some height energy, some gravitational potential energy, and then it'll be moving. So we've got that. So now notice here that the m's don't cancel out because we do not have an m. This is a kx squared over 2, not mv squared over 2. So we can't cancel out the m's. So plugging in for numbers, 1500 for k, the spring constant, x squared, it was compressed a quarter of a meter over 2. 5 mass times gravity times height, 5 times 9.8 times. Now we used the same quarter of a meter here because that was how much the spring was compressed from its natural state, and then when this is how high it's elevated when it reaches its natural state. So that's why we were able to use that number twice, plus 5 squared over 2. So anyway, velocity equals 3.7 meters per second. The next question is how high does it go? Okay, so I get to choose what I consider to be my initial state and my final state. I could consider this to be my initial state and this my final state, or I could consider the beginning state to be my initial state and that to be my final state. So I'm going to choose this to be my initial state again, and we'll just start out with one type of energy. When we're in this state, we only have spring energy. So we only have spring energy here. Now when we're here, we want to look at what type of energy we're going to have. Will we have gravitational potential energy? Sure we will, because it's elevated above where it started, and we're looking for that distance, how high it is from where it started. Will it have spring energy? No, the spring is uncompressed. Will it have kinetic energy? Okay, not at the maximum height. At the maximum height, it's going to be moving. It's not going to be moving at all. It'll be stationary for that split second. So plugging into our equations, kx squared over 2 plus 0, no kinetic energy, equals mgh plus 0 for the kinetic energy, and we get a height equals 0.96 meters. So, okay. Now we're going to go bungee jumping. So we're gonna start our own bungee jumping business, and we want to be able to give the bungee jumpers an exciting bungee jump. Okay, meaning we want them to get close to the ground, but our profits will be decidedly diminished if they hit the ground. So we do not want to let them hit the ground. So we want to use a little bit of math, and we want to try to figure out how high the bridge needs to be above the ground in order for them to get close but not hit the ground. So now we're going to use a bungee cord that's 15 meters long, unstretched. Okay, and the spring constant of the bungee cord is 50 newtons per meter. Okay, and we want to figure out how far above that bridge are they going to descend at their very lowest point. And when that bungee cord is stretched to the max and the velocity is 0. So we want to figure out, we're going to look at, I guess we're going to look at y, the distance stretched. How far is that bungee cord going to stretch? And that sort of thing. So what we're going to do is we're going to consider, we're going to solve for y in this case. Instead of looking at the total distance, we're going to solve for the distance stretch. No big deal. So we're going to look at the type of energy we're starting out with. Are we starting out with spring energy? No, the bungee cord is not stretched. Okay. Is the bungee cord, do we have any gravitational potential energy? Yes, we do. Okay, and the total height, we're going to consider this to be our ground state, the lowest point that the bungee jumper goes. Okay, so back to this. Sorry, I got interrupted here. So we're originally starting out with gravitational potential energy. So no spring energy, no kinetic energy. So we've got mgh. Now our height is going to be 15 plus y. As again, we're considering this to be our 0 state. So we chose our variables carefully because this is an important quantity to know. So we got that. So we're going to skip this middle state. It doesn't really matter to us except for the fact that the stretch is 15, or this extends 15 meters before it stretches. That's the natural length of it. Then when we reach the bottom, okay, do we have any gravitational potential energy? No, because we consider this to be our 0 ground state. Do we have any spring energy? Yes, we do. Okay, and what we're going to use for our x is going to be the y. Okay, we're not going to use this full distance because it unraveled 15 meters before it started to stretch. So this is where it started to stretch. So our distance y is what we're going to use for our kx squared over 2. Okay, so does it have any kinetic energy? Not at the very bottom, because he's going to come to a stop at this very farthest point. So let's just stick that into our equation. So our potential energy initially there's no spring energy, there's just gravitational potential energy, and that's at 15 plus y. That's our total height above where we're going to end up. There's no kinetic energy, beginning or ending. Okay, our initial our final spring energy is ky squared, okay, over 2. So distributing the mg and then putting it into y squared, y, and constant form, which should look a little bit familiar as the quadratic form. We can plug this into our quadratic solver, and we're going to get that y is either equal to minus 10.9, okay, or 40.3. So the minus 10.9 number we're going to ignore because it's negative. The 40.3 number is the one that we want. That's going to be our answer. Okay. Just a little bit before we move on here. I know this is kind of a longer notes. Just to touch on escape velocity. This is basically how fast you have to throw an object away from the Earth, or from another planet for that matter, for it to never come back. So if you throw it, if you don't throw it hard enough, it's going to come back down on your head. If you throw it hard enough, eventually it'll never come back. And so I've got a picture of a rocket. That's probably not really a good picture. Rockets don't need to reach escape velocity because they can continue to eject gas and can get thrust and can leave the Earth with not at the escape velocity, they could keep burning fuel and getting thrust. So they don't need to reach the escape velocity, which is quite high. I'm not going to make a big deal out of this. This is just one of those things that's on the AP objective. So I wanted to at least make sure I exposed it to you. Okay. So basically, what we want to do is we've got some initial energy, and we're going to compare that to our final energy. So our initial energy is going to be the gravitational potential energy that we start with. We're not talking about springs, so we don't have any business with that, kx squared. And we're going to be moving at our escape velocity initially. Okay, so this is our initial kinetic energy is equal to 1/2 m times our escape velocity. And remember, we briefly touched on this. I didn't make a big deal about this either. The potential energy, if the distances that you're going make Newton's law, universal law of gravitation a factor, your potential energy is gm m over r. So we're going to start with this negative gravitational potential energy, and then at the very furthest part, we're going to come to a stop at a distance of infinity away from the planet. We'll come to a complete stop at an infinite distance, but I guess ultimately we'll just keep going slower and slower and slower and slower as we get further and further and further away. So our distance r will be 0 at an infinite distance, and here we're at the distance r, which is the radius of the planet. So the escape velocity is equal to 2g m over r. So this is how you calculate how fast something needs to be moving to leave the surface of the planet and never come back. Okay, and that is that.